let us begin. So today there will be 4 parts, and the part number 1 is about the support function. So as yesterday, K will always be a convex body in RD. And the first definition is so I define a support hyperplane so this is any hyperplane which intersects K but does not cut it into two parts. So such hyperplane that K lies completely on one side of it, but it has a common point, at least one common point with K. So support hyperplane is any hyperplane H such that H intersection K is non-empty, but K lies on one side, lies in one of the half spaces. One of the half spaces bounded by H. So the easiest thing is to draw, of course, two-dimensional pictures. So this is a convex figure in the plane, and so if the boundary is smooth, then a support hyperplane is just a tangent line in this case. So, but if we take something non-smooth, so let's take a triangle, then there are many, well, in this case it's not a support hyperplane, support line. There are infinitely many support lines that go through this vertex. So all these are support lines, but there are also support lines which contain an edge of the triangle. So good. Then the following is a simple lemma. One can find a support hyperplane with any direction. So for any vector V in RD, but I need to take out the 0. For any non-zero vector, there is a unique support hyperplane with the outward normal V. With the outward normal V. So we can prove it, but you can also illustrate it by a picture. So some convex body, and I have a vector V. Then what I do in order to find a support hyperplane with this normal, I just move hyperplane until it reaches here the top of the body. So then this hyperplane has the outward normal V. So by outward normal, I mean that the normal points away from the body. Right, and the proof, the following proof is just what we are doing. We are maximizing a linear functional over the body K. So maximize the function x goes to inner product Vx over the body K. So good. And now we are ready to define the support function. Well, so the support function of K is a function denoted by h sub k. It is defined on Rd and takes real values. And, well, hk of v is basically the maximum value of that linear function. hk of v is maximum over all x in k of maximum of the inner product Vx. Okay. Well, and this is defined now also the zero vector. So, for example, hk of 0 is just 0. So, hk of 0 is 0 by just from this definition. And this function has a geometric meaning. Well, what it is basically the distance from the origin to the support hyperplane, but for that one has to assume that V has norm 1. So geometrically, if the norm of V is equal 1, then h sub k of V is the distance, but distance with a sign. So the signed distance from the origin to the support hyperplane. Support hyperplane with the outward normal V. So if I almost copy this picture, well, I better erase this picture and draw another one. So I have a convex body and assume that the coordinate origin is somewhere here. Okay. Then if I am given a unit vector V, then I'm looking for the support hyperplane with this so with this normal V, and I am basically computing this distance. So this distance, it is hk of V. Right, because this hyperplane, it is given exactly by the equation V in the product x is equal to what it is. Yes. And this distance will be negative if 0 lies on the other side. So this is possible if the body is here, if the 0 is here, and the hyperplane separates 0 from the body. Then the distance will be will have negative sign. So I mean the value of the function will be distance with the minus sign. Good. So that's the it's a very important concept for today and also for later. And we then look at some properties of this object in order to understand it better. So theorem. The support function is always positively homogeneous. And it is convex. So h sub k of lambda v is equal lambda times h sub k of v for lambda bigger or equal 0. That's positively homogeneous, and h sub k of v plus w is less or equal h sub k of v plus h sub k of w. So these are very good properties, right? So this is, and well, why is that? The proof is simple. So the first one is just take the definition, and the second one is also take the definition and think a little bit more. In the second case, somehow you, so first is obvious, and second, so we take what? If you take any point x in K, then we have, of course, v plus w in the product x is equal to vx plus wx. And now to compute the support function, we want to maximize this over x, right? So for x over k. So if you take the maximum of that over all x in k, then we get hk of v plus w. And at the same time, we want to maximize this. Maximum of the left-hand side is equal to the maximum of the right-hand side. But on the right-hand side, if you maximize the sum of two functions, the maximum of the sum is less or equal than the sum of the maximum, because maybe this function is maximized at one point, x1, and this function is maximized at point x2. So therefore, the maximum of the sum is smaller or equal. So let me write here, the maximum is less or equal than the sum of two maxima. And that's end of the proof. Yes? Equal 0 is also all right, because for 0, hk of 0 is equal 0. Therefore, if you substitute lambda equals 0, you get lambda k of 0 is equal 0 times, so that's. Well, one can say it's non-negatively homogeneous. But, you know, it's for French people, it means non-negatively. Well, let me just do that. And I have not lost anything, because for lambda equals 0, it's anyway clear. Yes, so the support function has these two properties, and in fact, any function with these two properties is the support function of some convex body. I will also speak later a bit about the connection with the Minkowski functionals, so which are also defined by convex bodies, but in a different ways, not as support functions. So conversely, any positively homogeneous, but then again the question of the 0, positive homogeneous, continuous, then it's 0 and 0. Positive homogeneous, convex. Convex implies then also, well, doesn't imply. Okay, positive homogeneous convex function is the support function of some convex body, of a unique convex body. Yes, of a unique convex body. By the way, note that I'm not saying that the function h is non-negative itself, right? I have not said that, I only say that it's positively homogeneous, but the values of H can be negative, right? Like in this picture. In fact, one can write this. So right now, so when is the function hk non-negative? So hk of v is bigger than 0 for all non-zero vectors v, if and only if the origin lies in the interior of the body. 0 belongs to the interior of K. So then the distances to all support hyperplanes will be positive if the 0 is not outside. So then some examples. The support function of a point. So the one point set is a linear function. So just by definition, h of the body, which consists of just one point p, hp of v is equal to pv for every v. What is the support function of a convex polytope? What? And convex, yes. So this is convexity. Actually, one can put here also any coefficients, and because of the positive homogeneity. But yes, that's actually a good point. So this together implies that h sub k of lambda v plus 1 minus lambda w is less or equal than lambda hk of v plus 1 minus lambda hk of w. So this follows just from these two properties by using homogeneity. Then that's convexity of the function. Right? So now the support function of a polytope. Well, so the polytope is a convex hull of a finite number of points, and any linear functional always attains its maximum in one of the vertices, so in one of the points. Therefore, this function has just finite number of choices which one of linear functions to take. So therefore, the support function of a polytope is piecewise linear. So that's because a linear functional attains its maximum at one of the vertices. But yes, I also understand the question of Mark-Schwab. That's usually called subadditive, right? So it's subadditive and positively homogeneous. And subadditivity plus positive homogeneity implies convexity. So that was not very not following the terminology, in fact. Good. So let us take an example of a polytope and its support function. So I'm drawing pictures in dimension 2, but for today it's enough for the illustration. So I take this triangle with vertices 1, 0, 0, 1, and 0, 0. Now I want to compute the support function of this two-dimensional convex body. Okay, so that is I'm taking any vector v, and I want to maximize the corresponding linear functional. Good, it depends on the direction of v. If v is between these two vectors, then the maximum will always be attained at this vertex. So there is another normal here, and the vertex which is the best depends on between which two of these three vectors the vector v lies. Therefore, we have to do the following. So we take again our two-dimensional plane, and we draw these normal directions. Oh, let me use now the colored chalk here. So we draw these directions. And then in this domain, the function, so for any vector v from here, the support function is equal v in a product with 1, 0, but xy in a product with 1, 0 is equal to x. So we have h of xy equal x here. Then in this domain, this will be the h of xy is equal to y. And let me ask you what happens between these two vectors. What is the function hk here? There is only a little place here, it's a place only for 0. So that's 0 here. Right, so this is a function which is 0 in this quarter, and then it is equal to the x. So it goes like that here, and it is equal to y, it goes like that here. If you take the graph, then you get a convex polyhedral surface. So now these properties, they are, so they remind, well, they are exactly the definition of another function. So the following fact is true. So I stated as a lemma, I will not say anything about the proof. So the support function of K is actually the Minkowski function of the polar dual body. The support function hk, well, support function of K is the Minkowski functional of the body K circle, so which is the polar dual. It is defined as the set of all x in Rd such that x product y is less or equal 1 for all y from K. But this makes sense only if the origin is in the interior. If 0 belongs to the interior of K. Because otherwise, if 0 is not in the interior, then this will become something unbounded. Minkowski functional, you know, so that's f of v is equal to the maximum value of lambda such that lambda v belongs to, so in this case, to the circle. So Minkowski functional of K circle. It is defined like that, and well, it requires some work to show to prove this lemma. So the support function of K is actually this functional of the dual body. And so this polyduality is also a very nice thing, of course. So polytopes become polytopes after duality. And for example, ellipsoids become ellipsoids. Smooth bodies become smooth bodies. Okay, so that's all that one has to know about the support function. The second part is the Minkowski sum. If you have any questions, just interrupt me and ask. Now that's a new topic, Minkowski sum. Well, so this is very easy. Here one needs only the definition. So for K and L subsets of Rd, the Minkowski sum is defined as K plus L is the set of all sums P plus Q, where P is an element of K and Q an element of L. This one can define it even for non-convex bodies. That's just the sum set of two sets. But if K and L are convex, then their sum is also convex. So that's a nice exercise on using the definition of convexity. And let us take two examples of Minkowski sums. Yesterday we had this body KR, so the set of all points at distance at most R from K, and this is in fact equal to K plus the ball of radius R. So B here is the unit ball, so that R times B is the ball of radius R. Well, B is the ball centered at the origin, so that's the set of all x such that the norm of x is less or equal 1. Good, so that's, again, one needs maybe to think a couple of minutes to see that this is true, but one arrives at that. Another example, if I take the sum of a body and a point, so 1 point set, K plus, I will just write x without the brackets, K plus x, this is just K translated by x. Is the translate of K by x. So maybe a picture for that, or if you have the body K and 0, say, lies here, and then somewhere I have the point x, so this is all the same plane, then K plus x is just a copy of this body, but where x takes the same position, exactly the same position as 0 has taken here. So this is K, this is K plus x. And here is the most important fact about the Minkowski sum. The support function of Minkowski sum is the sum of support functions. That is h of h sub k plus L is equal to h sub k plus h sub L. And this is, in fact, a simple theorem. So again, one has to maximize, right? So we take any vector v, and we take any point p and any point q. Oh, right, v first v, p plus q is equal v p plus v q. Now again, we take the maximum of this and the maximum of that. But this time the maximum is equal to the sum of two maxima, because these two maxima are taken over two independent things. So this is maximum over P, this is maximum over Q, and here is maximum over all pairs P and Q. So this Minkowski sum, if we, so it seems that we can at some point forget about convex bodies and just speak about support functions, which are convex functions, convex and homogeneous functions, and just speak about the sums of these functions. Okay. So again, it's useful to play with some examples. For example, take a triangle and take the sum of two triangles, of two different triangles, or take some polygon and take its sum with a segment. Because sum with a point, we know it's easy. What is the sum of a segment and the polygon? Okay. So now then, the next part is the Hausdorff distance. So I think some of you, so who does know how the Hausdorff distance between two sets in the plane in the space is defined? Now you will know, because well, this is not of course something from a standard course, but I just wanted to check. Maybe it's something well known. So for two compact sets, one defines the distance. I don't know if I write this line, is it okay for those sitting behind, or it's better to, okay, I write here. So the distance between K and L, anyway, this definition will be very, will be quite useless. But this is the definition. So this is the maximum of two numbers, and one number is itself a maximum. So maximum over all P in K of distances. So maximum of distances from P to L. Good. And then we take another number, which is the maximum over all Q in L of distances from Q to K. In fact, the distance from Q to K itself is defined as a minimum of distances from Q to X in K, so that the complete definition is even worse. So that's maximum of minima, another maximum of minima, and then you take maximum of these two maxima. But the definition becomes better if one explains it with a picture, and then it becomes even more, so even better. Okay, but first let us draw a picture. So this is a body K, and this is the body L. So what do we take first? We take the maximum of all points P in K of distances from them to L. So which point is the furthest point from L? So it's some point here. So this point, this distance is the maximum of distances from P to L. And somewhere here is the point Q, which maximizes distance to L. No, to K. And of these two distances, we take the one which is bigger. So say this one. So this is the Hausdorff distance between the two sets. But one can think more about this definition and prove the following. In fact, distance between K and L this is the minimal number R such that K is contained in the R neighborhood of L, and L is contained in the R neighborhood of K. Yes, by the way, when I write inclusion, then I mean also non-strict inclusion. So many people write this, but I don't write this, but still mean the same. I mean the possibly equality. Okay, so this lemma actually, it follows from all the definitions, because we know what is the R neighborhood. So these are all points that have distance at most R. So the distance, Hausdorff distance between K and L, this is really exactly that. So for distance to be smaller than R, you need that K is contained inside LR. And L must be contained inside LK. So that means, again, on this picture, if this is, so this length is the Hausdorff distance. Now if I somehow engulf K, so take the R neighborhood of K, then it will swallow all of L. And if I engulf L by the Hausdorff distance, it will also swallow all of K. So that's exactly actually the Hausdorff distance. And this implies that we can define, no, not yet. So now we make another step. We make another step, and we know what is the, no, okay, so I just state the lemma. In fact, in terms of the support functions, this distance is just the uniform distance. But for this, we need to restrict the support function to the sphere. Good. So distance between K and L is the L infinity distance between their support functions restricted to the sphere, so to the vectors of length 1. So that is distance between K and L is equal to the, so I take the function hk, restrict it, so it is defined on the whole space Rd. I restrict it to the unit sphere, to the vectors of length 1, subtract the function hl, also restricted to sd minus 1, and take its infinity norm. So that is the maximum of the absolute values of hk of v minus hl of v. Maximum is taken over all vectors v of norm 1. So that's exactly the definition of that norm. And the proof of that, well, K subset LR is equivalent to, this is what I did not prove, but one set is a subset of the other if and only if its support function is strictly less or equal than the support function of this. So this if and only if hk is smaller or equal or HLR, right, for all at all points V. But HLR is equal to, sorry, I want to finish here. HLR is equal to what? LR is the Minkowski sum of L with a ball of radius R, and the support function of the sum is sum of support functions. So what I have here is HL plus the support function of a ball. This is just a constant function. So this is just a function since I'm on the sphere. So all these functions are restricted to the sphere. And the support function of the ball restricted to vectors v on the sphere is just constant function r. Okay, so what we get is that K subset LR is equivalent to HK minus HL is less or equal R. Now if I take these two conditions together, then I get that the distance is indeed just the maximum of the absolute values between these differences of the functions. Good. So that means if you go to support functions, then all these things become something very natural. So Minkowski sum is the sum of functions, and Hausdorff distance is the L infinity distance between the support functions. Okay, so far so good. Any questions? Well, so since there was not enough place on the blackboard, it remains an exercise. So there are remaining steps, but that's a useful exercise, just to think about these definitions. Good. So let us see what we need next. So now I want to prove one thing that left unproved yesterday. So namely, I will prove the Steiner formula in its full generality. For this one, well, one needs not much. One needs first the following theorem. The volume is continuous with respect to the Hausdorff distance. Hausdorff distance. Well, so the proof is a bit technical, and I just don't want to spend time on that. But somehow, so if this is a body K, so this is now some hand waving. So if this is K, and I take any L at a distance at most epsilon, no, most delta, then this L must be contained in the delta neighborhood of L. So we must show that. Well, and on the other hand, L. So it's not good to take the inner neighborhoods because they can become non-convex at some point. But L is somehow between. So L is somehow between K minus delta and K delta, and one has just to show that then the volume of L does not differ from the volume of K much. And that's, well, so then there are some other technical steps, and that's not really interesting, but it's quite plausible that if you are inside this ring for very small delta, then the volume of the body doesn't change much. So as delta goes to 0, then epsilon will also go to 0. Okay, if one believes this theorem, then the proof of Steiner formula goes as follows. So first I state this Steiner formula again. So we say we want to prove that for any convex body K, the volume of its R neighborhood is a polynomial in R, polynomial of degree D. So there are some coefficients AK depending on K. And besides, what I didn't state yesterday, besides these coefficients depend themselves continuously on K. So this AK of K depends continuously, again with respect to the Hausdorff metric, on K. In fact, from this formula, the continuity follows easily. But the problem is that in order to prove this theorem, I need the continuity of the volume. well, not absolutely easy, because again there is a problem with this inner bodies, and that's well. But one is tempted to use Steiner formula of the continuity, which is unfortunately not allowed. Okay, so the proof. So first, if K is a polytope, then, so I hope I convinced you last time, so yesterday, that the R neighborhood of any polytope can be cut into pieces. And the volumes of these pieces, so they are actually the coefficients there. So this is just volume itself, so it contributes the constant term here. So this volume is linear, and this volume these parts have volume which is quadratic in R. And the same works for in any dimension. So if K equal P, I will denote polytopes by P now. If K equal P is a polytope, then this follows from from cutting P into pieces. Like that. Now, if K is an arbitrary convex body, then it can be approximated by a polytope. So there is a sequence of polytopes converging to K. So for a general K, take any sequence of polytopes converging to K. So sequence Pi. So I will put the indices of the sequence above, because I will need to take the R neighborhood. So Pi converges to K in the Hausdorff metric. But this implies that the R neighborhoods of these polytopes also converge to the R neighborhood of the body K. And why? What do we know about the Hausdorff metric? We know that it is the uniform metric on the support functions. But in fact, the support function of this minus the support function of that is exactly the same as the support function of this minus support function of that, because this support function has this plus R term, and so this becomes trivial. Good. So if this sequence of polytopes converges to the body, then also this, for every R bigger than 0, the R neighborhoods converge to the R neighborhoods. Now, because of the continuity of the volume, this implies that the volume of Kr is equal to the limit of the volumes of PIR. But each of these volumes is a polynomial. So this is a limit as I goes to infinity of the sum of AK of Pi times R to the power K. And the sum goes over K from 0 to D. So what we have proved is that the volume of Kr is a pointwise limit. So because this is for all R bigger than 0, is a pointwise limit of polynomials. What functions are pointwise limits of polynomials? Well, actually all functions are pointwise limits of polynomials, but in this case we have polynomials of bounded degree. And if you have a sequence of polynomials of bounded degree, then they can converge pointwise only to polynomials. That can be proved. And besides, the coefficients of these polynomials converge to the coefficients of the limit polynomial. So polynomials of bounded degree can converge converge only, well, sequence of polynomials of bounded degree can converge only to a polynomial, and the coefficients converge to coefficients. And this proves the Steiner formula. And since yesterday we have seen the meaning of these coefficients, a, k, in dimension 3, so it gives all these things that I have stated yesterday, that if you have a smooth convex body and you take a sequence of polytopes converging to the smooth body, then this sum of angles times lengths, it converges to the integral of the mean curvature. So this is now proved. And this also means that so this sort of total mean curvature can be defined for any convex body, so which may be not a polytop and also not a smooth body. Okay. Any questions? No. I have 35 minutes. 5 minutes? 5 minutes. Are you sure? No, but so it was 16 till 5:30, no? Ah, but I believed what was written. And I have okay, so then I state some theorems, and so you will have homework. So you must solve them within 30 minutes. And namely, so who said that it's just 1 hour, Jotana? So you have to solve this. And if anybody has questions, then please ask Professor Papadopoulos. And since I want to punish him even more, I will give some formulas. So part 4 is some formulas. Good. So there are 4 formulas. 2 formulas in the first theorem. So the volume of any convex polytop is given by, well, is equal to d, so d is the dimension of the ambient space. And then there comes the sum over I from 1 to n, hi times the volume. Well, so this was the d-dimensional volume. Now here I will take the d-1 dimensional volume of fi. So where, what is hi, what is fi? So fi's are the maximum dimension faces of P. Well, so you know this formula in dimension 2 and dimension 3, in fact. So if you have a polytop P, so let me maybe explain it then by picture. So this is 0, then every polytop has a finite number of facets. So fi are facets, and the facet is a top dimensional face. And what is a face? A face is intersection of polytop, well, actually of any convex body with a support plane. intersection with support plane, support hyperplane. So facets of a pentagon are its 5 sides, and so this is Fi, and Hi is the corresponding, so the support function evaluated on the normal. Good. So Hi is Hp of Vi. Well, that's very a lot of notation, but the picture actually explains everything. It also explains the formula because the area of this triangle is equal to 1/2 Hi times Fi, right? That's the proof of the formula. Then there is the volume of any convex body is equal to 1/d, the integral over the boundary of K of the support function. Well, and the integral is done just by the area element, of the boundary. Right? You can note that these two formulas are very similar because the integral is also a sum, and the area, so this is area of a small piece of a boundary, and here we also have taken area of a piece of a boundary. Then
in the formula,
Hi, yeah, so Hi is explained by this picture. This is the support function, the value of the support function on the normal to the face. Well, it's just the distance from the origin to the plane spanned by the face. Well, somehow that's again the definition, but one has to explain what Vi is. And okay, so then two more formulas. Again, for any convex polytope, one has the sum over all I from 1 to n. So n is here the number of facets. The sum of volume of the ith facet times the normal to the facet. So Vi is what is thrown there, so that's the outward unit normal to the facet. And this sum is equal to 0. So in fact, this is these are D equations because Vi is a vector, so this is a vector 0. And another formula for smooth convex bodies. That's yes, D minus 1. And here we must take the integral over the boundary. Actually, again, so we can just look at this. So we want, so this is the sum of unit normals. So here we'll take the integral of the unit normals. But the unit normals, I mean, to integrate, you need to have a measure. So the measure is just the area measure on the boundary. So that's the integral of the normal vector, the area is equal to 0. So if I take any convex body, take the unit normal vector field and integrate it, then the integral is 0. And actually there is a physical proof, because if this is a balloon and it is filled with an air, and not a hot air balloons, because a hot air balloon will fly. If the air has the same temperature as outside, then the balloon will not fly anywhere. And it will not fly anywhere because the sum is 0. Because this integral is the total pressure from outside the balloon, from inside. That's a very, very, it is made from a very stiff material made in Switzerland. So this is really some, okay, so even it expands, so let's assume that it's now in equilibrium. So everything is in equilibrium, but there are still forces from outside, and they are equal exactly to this integral, of course. But I mean, that's not a satisfactory proof, because actually this theorem that the balloons don't fly, so we have to prove it and prove it mathematically. And there is so there are proofs for these theorems. Okay, then that's it for today.